the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and the Physics podcast. I'm your host, Parker.
And I am Ray, and we welcome you to an episode. No, wait, it's episode 30. 30, the big 3-0. Today we're going to be talking about something pretty interesting. We're going to be talking about an idea, just two people talking, on how physics could have been invented.
But hold your horses.
Sorry?
We're not starting just yet.
Oh.
We did just recently hit 10,000 downloads. Let's go.
No way! Clapping sounds in the background. Clapping sounds in the background.
After how many? Oh, wait. Today, we posted our first episode the May 9th. So it's been how many months since we started? Because it's October 9th today.
Oh, that's crazy. How many months
Today's
the day.
Wait.
Is today the day?
Wait.
We're not sure.
It's been 5 months since we started.
Okay, it's been 5 months since we started. I think that's pretty crazy. To be honest, I mentioned this on our Instagram post, so if you guys are listening and not following our Instagram, go follow it at Math and Physics Podcast, at math.physics.podcast, where basically Parker and I thought that we would reach 10K by the start of 2021 when we began the podcast. And
not even the start. We thought it was going to be like March.
Well, yeah, to be honest, we thought it was going to be like almost next year. But here we have it in October, reaching 10,000 downloads. I think that's pretty insane. Thank you.
Yeah.
Thank you to everyone.
Because back in like when we first started, we were getting like 1,000 downloads per month. So we're like, okay, 10 months from now, we're going to be at 10,000.
That made sense back in the day.
Yeah.
Were we wrong?
But,
Also, it's, as I was saying, number of episodes as well. Now we're going to be, as we have kind of come into this weekly schedule, I think it's kind of nice. So we should be very consistent now.
Yeah.
So, yeah, it'll be good. It'll be very good.
Also, one more thing. I was listening to an older episode of the podcast. It was episode number 19. This was Alien Math, okay? So this was 11 episodes ago. I had announced in the beginning of the episode that we just hit 120 followers on Spotify. And, fast forward 11 episodes / 11 weeks, we're at 759 followers.
Wow, that's crazy.
Spotify.
That is crazy.
So yes, thank you to everybody that's been following the podcast and listening and all of that stuff. We love talking about physics and we love talking about math. Mm-hmm. And our goal is just to spread the knowledge of these topics. And so next episode is actually going to be a 10K Q&A special episode. So if you guys want to leave comments or questions. Your questions, you can leave them either like YouTube, the YouTube comment section, or on our Instagram, which Ray already said. It's math.physics.podcast.
You can email us at uft.math.physics@gmail.com.
Anyways, all of the information is going to be in the description. So
So
thank you to everybody.
Absolutely. 10K Q&A coming up. Woo-hoo.
That's right. And we're very excited to hit 1,000 followers.
Not just yet, but hopefully soon.
Yeah, probably in the next, I would say 1 month.
1 month? You think so?
Easily within 1 month. Because we've been getting 200 followers every 2 weeks.
Oh, discussing stats with the audience. I like this.
Yeah.
I like this.
Which is pretty cool. So
we're very open people.
Yeah, definitely within the next month. So let's
see. Okay, cool. I mean, our goal to reach 1,000 is before next year. That's our goal. Because I think, to be honest, we didn't really expect hitting 1,000 in this year. But now that we're decently close, I think we can smell it. So I think it's safe to say that hopefully if everything goes as planned, and so far it is, we should hit it by the end of this year, I think.
Okay. I guess we've wasted enough of your day. So let's actually get started into this episode.
Podcast.
So inventing physics.
Yep.
Why is physics so natural? I guess, is one of the questions I wanted to answer, because in essence, physics itself, or I guess classically, physics is just, a bunch of symbols on a paper that just describe observations of the physical world. I guess that's why it's called physics, after all.
The physical
we
world.
We say, okay, the heavier an object is, the harder it is to accelerate, right? So there has to be some relation between the mass and the acceleration, and this force that we need to accelerate the mass. I don't know if that was like circular reasoning or whatever, but we made observations and we wrote them down in a way that can be easily manipulated, aka, using the language of math to write down these relationships.
I think math was a very big help in the invention of physics. Definitely an integral part of math. That was a joke.
Integral part of physics.
Oh, sorry. What I meant is math is an integral part of physics. Sorry, that's what I meant. Yeah. So I just think math as a language itself, as we've spoken about it before, definitely helps us describe these observations, right? And the entire classification of physics just depends on, as you very well said, experimentation and observing these experimentations. The entire point of science, technically, we can kind of broaden the spectrum here, is to be able to experiment on something, conduct a certain experiment, and that experiment should be able to be repeated by any number of people anywhere in the world with the same conditions, of course. So the entire point of science is basically to convey your idea to multiple people. And hopefully, if that idea is correct, multiple people will start using it in their daily lives as what we call laws, right? Laws of science. Laws. And
this is why postulates and theorems,
axioms,
they state some kind of relationship that has yet to be contradicted, right? And that's what is so powerful about these statements, is that they have yet to be proven wrong. Thing is, a theorem is a theorem, right? It's been proven, it's been repeatedly trialed, tested, and it has stood the test of time.
But to be honest, we never really know what can happen in the future.
Yeah, because in the future, if, of course, we discover something crazy, like, quantum mechanics, but the quantum mechanics of the future, that just breaks quantum mechanics itself. Some things are going to be proven wrong that we thought could never actually be wrong.
Yeah.
What I'm trying to say with this whole discussion is that, and this is going to get a little bit philosophical, but basically, as an individual, you experience life through your eyes and your own, silent monologue in your head. And, of course, you have sensory inputs. And, one of the biggest assets you have is your memory, being able to remember things that happened in the past. But in reality, you don't really know for sure that the physical world is real. What tells you that atoms actually exist? The only thing that actually tells you that atoms exist are people at school that say, the world is made up of these small little particles that you can't see, but that's just how it is. Why? Because we have experiments that show you that it's the case, right? You could never tell, or not that you can't tell, but just using your naked eye and, your hands and your ears, you can never actually tell that atoms exist.
That's true.
But with the tools and the what am I trying to say? The group not the group, but the massive knowledge that has been acquired throughout the years of just scientific advancements, using all of that, you can then conclude that some things do in fact exist, like black holes, for example, or neutron stars.
The interesting thing, though, about a lot of these experiments is that sometimes, a lot of the times actually, the theoretical part of it, or the theory, is developed before the experiment. But sometimes, which is actually very interesting to see, where you observe something and then make a relationship to satisfy the observation. So there are kind of two ways to go about kind of writing, quote unquote, writing a law or a theory, where you can either observe something happening and then write down something that makes sense of that event, or you can think of a theoretical model and then search for the rest of your life for if that model exists. And that was actually most of physics, where special relativity, general relativity, Einstein didn't have ways to look at light. They didn't have ways to measure the speed of light, like experimentally. The only thing he could do was jot his ideas down on paper. And that theoretical model from paper is what helped us to then discover and then experiment and then observe all of these different natural phenomena. And so the theory sometimes, a lot of the times, helps or sometimes causes the experiment to be observable, or at least for us to understand it,
Yeah. I think one of the most incredible things about general relativity is being able to visualize these ideas, because, the curvature of space-time is not something that's just, easily representable like a graph on a whiteboard, but the idea that four-dimensional curvature is something that we're living in right now is just absolutely mind-blowing. But that it is what it is. It's a quote unquote fact of reality, the universe.
Of the universe. And I think a lot of times for a lot of people who have questions about these theories, questions about these laws, and a lot of high school teachers either don't know or just don't really care about explaining it. So a lot of the times, as you just said, they just said, it is what it is. That's just the law. Just learn it. But the people who actually want to understand the law, and those people are very interesting people in my opinion, because those are the people that actually want to get behind what is happening in the law and why it makes sense. And I think that itself is more important than just knowing that this thing exists. And that is why making, for example, general relativity, we learn it in a master's level course, or usually PhD, right? But Einstein, it took him 10 years of straight work.
Wait, that's not accurate.
Sorry?
That's not accurate. There's a general relativity course in
it technically is an undergrad, but it's focused on in masters. But what I'm trying to get at is that we can do it in a year. We can do a general relativity course in a year, right? But Einstein took 10 years just for general. Remember, you're also adding special, because technically it has a lot of parts about special as well. Yeah. So you're taking 15 years. That's a lot of part of your life
and
to figure out a theory.
And also, he's way smarter than a lot of people studying it right now.
That 15 years for him is a lifetime for most other people.
Yeah, what I think is kind of crazy is that there's two pillars. Wait, correct me if I'm wrong, but in the current modern description of the world or the universe, there's two pillars, right? There's general relativity and quantum mechanics. Yeah. Right? Take in, one man came up with one whole pillar, right? one dude came up with general relativity.
That's true.
And then there are a lot of people that have worked on quantum mechanics, right?
Very many.
Einstein himself, right? Einstein
actually rejected the idea of quantum mechanics.
Yeah, but he was part of like the discussion, right? Like
he was part of the discussion in the sense that he would be like, it's not real. Like that's the way
no,
he
no,
would
no,
participate in the discussion.
In a sense, he contributed because photoelectric effect, right?
Well, yeah, I mean,
As
technically,
well as
okay, sure,
quantizing,
of course.
quantizing the energy of photons. So he contributed to the world of quantum mechanics, but also, you know, Schrödinger off of the top of my head,
Dirac,
Niels Bohr,
Young,
also his, even going back
Michaelson, Morley, both of them.
back to the time where quantum mechanics wasn't even a thing. Huygens, you know, one of the dudes that did the double slit experiment.
Yeah.
You know, back then they had no idea what light really was.
Yeah, that's
because how do you study light, right? Like I want you to sit in a room with a light bulb and tell me what light is. You know,
like how would you be able to generalize what is either hitting you or reflecting from something?
It's not like doable.
Yeah, like, or at least by us. I mean, it was doable. It was done by Maxwell.
Yeah,
but
no, but technically,
yeah.
Technically, yeah, it was done, but not just, you know, with people like individually staring at a wall, you know. Or
I mean,
wall,
yeah, it's
like
all about theory. It's all about papers. It's all about, you know, it's all about the math. You can't really grasp the physical. Well, technically now we can. I should say that. But like back then, you couldn't really grasp the physical idea of an electromagnetic wave, right?
Yeah, but think about, like you said, before, when they were doing the double slit experiment, like what would you conclude from that? You'd say, okay, light is a wave.
But see,
and then
I mean, I don't think. Oh, I mean, it all depends, you know. Like, if you were to give me the double slit experiment and never tell me anything about it, like no knowledge, the fact that light is a wave or anything, right? Or like a general human being, or like a general scientist, I should say, actually, would they be able to discern that light is a wave? That's an interesting question.
Well, not without like tools.
Yeah, because the experiment gives an interference effect, but the entire idea of interference effects comes up with the knowledge that something is a wave. So I guess if you had ideas of what waves are and how waves behave and how waves interfere, and you saw this interference pattern on the screen, then I would guess that you would be able to deduce it as a wave.
If you don't know what waves are mathematically, then you wouldn't really make anything.
Don't know what you would do.
Well, no. Obviously, it requires some,
of course,
some level of understanding. But when you get to that point, obviously, you need, you know, to set up the double slit experiment itself. You need to know something about physics. No one's just gonna randomly put two slits on a thing and be like, "Oh, look, an interference pattern." Like, that's not really how it happens.
Yeah.
Other than that, yeah, I kind of wanted to talk about notation. As well.
We can talk about a little more experiments if you want before we get into there.
Sure, yeah.
Like when we're talking about the invention of physics, right? I'm just thinking about like different experiments. For example, like the one we were discussing in class the other day, right? And the one we were discussing before this, the Michaelson-Morley experiment. So for those of you that don't know, the Michaelson-Morley experiment was, okay, I don't actually know when it was done. It was pretty long ago, though, I believe, because the conception of light was very different back then. Because what people thought, it was that light propagated through a medium, right? And that medium was called the ether. So back in, once again, I'm not exactly sure. Parker, can you like search it up? What year the Michaelson-Morley experiment was done?
Yeah, you said conception of light, by the way, but it's perception.
Perception, sorry. The perception of light, yeah, sorry. So they thought that basically the universe consisted of this eternal thing everywhere called the ether. And the only way that light propagated was through the ether. Because obviously
1887.
Sorry?
1887.
1887. Yeah, so people really didn't know that light goes in vacuums, travels in vacuums. They didn't really know that existed. They didn't know that light can travel in various different types of mediums. So they suggested the idea of an eternal medium called the ether. So the Michaelson-Morley experiment is a basic interferometer where, and we did discuss this in the quantum mechanics episode, so that's awesome. So it's a basic interferometer where we're measuring the light that's traveling in a perpendicular and a parallel direction. Now, if the ether exists everywhere, they suggested the idea that the ether is constantly moving in a singular direction. So if this is true, then the perpendicular and parallel light rays should have a interference pattern because they won't be coming in at the exact same time, right? And you should detect some light in the interferometer. However, after repeated trials of the experiment, the light always returned at the exact same time. Noting and therefore kind of not exactly proving, but hopefully making them understand that light doesn't need a medium to travel through, and it travels the same speed in the same medium wherever you are in the universe. So that was a pretty cool experiment too, that I felt like we should talk about.
Yeah, it's pretty dope. But I want to make like these episodes less technical, so more people can actually understand it.
I guess that's true, but I mean, we did speak about interferometers, I think, pretty decently in the quantum mechanics episode, right?
Yeah, but obviously, like that's also an episode about quantum mechanics.
Yeah, that's true. That is very true. That is very true. Yeah.
So, moving on to
notation.
Yeah, I wanted to talk about, not really understanding mathematics, but kind of understanding why math looks how it looks.
Okay.
In a sense. So, for example, or I guess not, maybe not, but we denote functions, right? I'm gonna assume that everyone knows what a function is. Okay. Usually we denote a function like f of something, f of some variable is equal to some value.
Some value or some function or something like that.
Right.
Yeah.
Well, the function wouldn't be equal to a function.
Well, yeah, I mean, the function it outputs a function is what I meant. Like it equals an output.
Right.
Yeah.
So what I'm trying to say is that why do some people prefer some symbols over other symbols? Or, some way of writing an expression over another way? Because in a sense it's arbitrary, right?
Yeah.
It's just a marking with a pencil.
Yeah.
So for example, an example of notation that we learn in school, we learn both versions, right? There's the Leibniz notation for Leibniz. I don't know. I think anyways. So this is to write like a derivative, which is just the instantaneous rate of change of a function. You would write df, which is f is the function. So a small change in the function df, and then divided by dx, let's say. It just depends on the variable you're using.
Yep. Mm-hmm.
So we have df over dx. But what does that really mean? Why are we using 4 letters to represent something that could be, written as 1 letter? For example, F prime, which is Newtonian notation, I believe.
Oh, is that what it's called?
I think Newton was using the prime notation, and Leibniz was using the dy dx.
Maybe I'm not exactly sure, but that sounds believable because I don't think Newton used Leibniz notation. So
no, they were kind of beefing at the time.
Yeah, they were fully beefing at that moment because everyone was like, "Who invented calculus? Was it Newton? Was it Leibniz? Oh no!"
Yeah, and I don't think there's a consensus on that still, right? A lot of people ignore Leibniz because Newton is just this.
Newton is just god. A bigger scientist, just more political power, more power as a scientist in general.
Yeah, he's more recognized.
Yeah, exactly.
But there is definitely an argument to be made about Leibniz because he is like if you look at the actual things that he's done, he kind of has a case for him inventing calculus. The only problem is really who did it first.
Well, Newton started with integral calculus, did he not?
Yes.
I'm pretty sure he did, right? And
I think that's like some fact I heard somewhere.
Yeah, I'm pretty sure he started, like, he literally developed integral calculus at like age 25 or 26 or something like that. That's crazy to think about, by the way.
That is insane.
Just think about you invent a literal language of math before you turn 30. Yeah. Like, that itself is insane. Anyways, so apart from that, so Newton, I'm pretty sure, started with integral calculus. And Leibniz, well, he probably didn't, right? Because his entire notation forms from a derivative. Mm-hmm. So I'm assuming Leibniz did not use integrals.
We're deviating right now from
we're deviating
from the whole point.
We're still talking about notation. We're just talking about different types of notation. Because I think Leibniz notation versus Newton, like the f prime versus dy over dx. Mm-hmm. Like, I think that itself, that's a pretty big difference, because I think dy over dx just represents the function in a much more understandable way. Right, df,
I do think it's more descriptive of what's going on.
Exactly. Like, df is telling you it's a small change in f. Dx is
a
for
small
people who
change
don't
in
know,
x.
It's understandable.
For people who don't know, when you say like dx, the d basically, how I remember it, I just think of the d as saying differential.
Yeah, that is what it is.
Yeah,
it is a differential.
Well, no, it doesn't literally mean differential x.
No, obviously not. But it's the differential of x, because it's a differential is like the difference in. It's like the difference. The differential is another way of saying it's the difference between. So
no,
dx
but really
is
they could have used any variable.
Mm-hmm.
Yeah. But anyways, so dx means an infinitesimally small increase on the value of x, and then same goes for whatever you put after the d. Mm-hmm. And so, as we all learned in high school, when you have a linear function, just a line, to find the rate of change of that line, you do rise over run. Mm-hmm. But since that's just a straight line and the rate of change never changes, you can take any 2 points on that line and then do the difference in y divided by the difference of x.
The classic.
So, right? Rise over run. Yep. But when your function, your relationship is a little bit more complicated, you need to, study the instantaneous rate of change. And so the only way to do that is instead of taking the change in y over the change in x over some long interval, you approach those two, that interval basically to zero, and you take an infinitesimally small change in y, and then you divide that by an infinitesimally small change in x. And then to actually describe that, I think it's kind of unfortunate that there's an easy way out for derivatives.
I was actually just gonna talk about the fact that how the derivative laws just kind of breaks the whole conception and just makes us think in computation, which is kind of sad.
Like the derivative is telling you, a property about the function at some point. But, not sadly, of course, this is an advantage to have these formulas that can, it's a formula to give you the rate of change of another formula, right? Yeah. But, it turns out it's very easy to take derivatives of functions. There are rules that you can follow, by the letter. You just apply the rule and you get the derivative function for the original function. I think a little bit on the bright side is that this kind of makes integration, which is the opposite of differentiation. If you have a curve describing the rate of change of a function, you can then integrate to get a family of functions that is described by that derivative. Mm-hmm. And I say family of functions because you may notice that the rate of change of a constant function is 0. And so if you add any constant function to another function and take the derivative, it'll be the same. Yep. Right? So the family of functions is actually just the same function, but being translated up and down, because
basically
that has
just
no
a
effect
variable.
that has no effect with the value of the rate of change at any point x. All that to say, notation.
Notation.
So
Very
we've only
important.
been talking about like notation in calculus, but we could also be talking about like numbers. Numbers themselves are notation, and operations, plus minus, divisions, square roots. Why do we draw like a square root, like whatever? How do you describe that? Like
That's
a check mark.
True fact. Why do we
Like
draw it like that?
Why do we draw it like that? I don't know.
I actually don't know.
I honestly prefer using the power, like power of 1/2.
Oh yeah.
Because it makes it more natural, I think, when you're dealing with squares, cubes.
Yeah, especially when you're dealing with like cube roots inside cube or something like that.
Yeah.
Like it definitely, I totally
That's
get
right.
that. Like sometimes it can be a little bit too messy. So
And
but the interesting thing about notation is that all of notation was literally invented to make math easier.
Yeah.
Right? It was made by us to make things a little bit simpler to understand, a little bit simpler to grasp. In the same way that we have derivative laws, like why do the laws exist? Because there is no physical way to calculate the value, the instantaneous rate of change. Because again, the denominator approaches 0, right? That's why we use the limit and everything. And that's where that comes from.
Yeah.
But the entire idea of derivatives and laws and all these things are mainly just to help out the understanding or the concept or the perception of what math can do. Yeah.
Very true. One other aspect to notation, or not really an aspect, I guess, kind of like a facet, is something that we're learning right now.
Oh, are you going to talk about notation? Oh no.
Yeah.
Wait, did you say Dirac notation?
Yeah, Dirac notation.
I thought you said that. Yeah.
Which is, I don't know if you've probably seen it, but if you're in the math world, if you're in the math world, you might have noticed like a straight line, and then some variable, and then an angle bracket? Is that how you call it?
It's like a greater or equal to sign, like that.
Yeah, kind of.
Basically. Yeah.
Anyways, that's just basically, instead of writing vectors, which once again is all notation, right? The idea of a column vector and a row vector, they're not actual columns and rows. They're just it's just a collection of numbers that we happen to arrange vertically versus horizontally. But it's the power in the notation comes from not the coincidence, but I'm looking for a very specific word. It's the fact that the reason why we put them in columns and in rows is because it makes the operations easy. Like dot products, you can just imagine the row going into the column or something.
Exactly.
Or no, sorry, the column going into the row.
No, it's the row, the column.
Anyways.
Anyways.
All that to say is, convenience. That's what I meant to say.
Convenience. Yes.
Yeah,
yes, definitely provides a lot of convenience.
The reason we have this powerful notation is because of the convenience. And I think that's one of the main driving forces that pushes people to choose one type of notation over the other.
And I think that's also why a lot of times in high school, when some teachers, say you can't use that way, you have to use this way, and you're like, why?
Yeah, that's
math
ridiculous.
is math.
Yeah, that is ridiculous.
No, even though it is ridiculous, I'm not gonna lie. Some of the high school teachers are definitely like, you can definitely use certain ways, like they're okay. But sometimes there definitely are certain, types of questions that do not require, but if you do it in a certain way, it'll be a lot easier to understand and it'll be a lot easier to answer. So sometimes, believe me, even though it sucks to say, okay, I'll change my method to a teacher, sometimes it is actually worth it, because there are situations where some notation, as Parker was mentioning, is just easier to use than the other, even though they mean the exact same thing. And there can just be advantages and disadvantages for each different notation, right? In the same way.
Yeah, I have an example of that.
Okay.
Where I was using some kind of notation in high school and I switched it in university. But I can't remember what it is. But I remember thinking about it back in first year. I was like, man, like in every single one of my classes, they were using this one notation that I wasn't used to. And I just decided, I'm like, okay, you know what? I'm just going to switch to it. And obviously I'm still using it now. Because it's just a personal preference, to be honest.
Yeah, I mean, and that's actually another point. A lot of notation is just personal preference. Because
also, I think it's a matter of tradition,
especially with Dirac notation or Dirac notation. For those of you that have come across it before, you might know that there are two ways of doing it. You can either solve it in Dirac notation or using matrices. And for some people, matrices are easier to use. For some people, Dirac notation is easier to use. So it all just depends on personal preference and what type of question it is, and it's all subjective, mainly. Yeah.
I think I have two conclusions to draw.
Okay.
First conclusion is, this is why, if you go and listen back to our alien math episode, this is why alien math could literally look like absolutely anything, because notation is just a personal preference. They could have chosen absolutely anything to represent absolutely anything.
Exactly. Infinite
and the
combinations.
The second conclusion I wanted to draw was circling back to inventing physics.
Oh, the main one. Conclusion.
Where notation has a very big role in inventing physics.
Definitely.
Because it kind of defines how the future people, the future physicists and mathematicians are going to I don't want to say develop their ideas, but kind of the notation draws a path. And, most people just stick to that path and then keep walking in that direction.
I mean, some notations are bad, like some notations you're just not comfortable with, and it might not, get bigger in the future. But some notation, for example, Dirac notation, was used to, help classify quantum mechanics. And now it's used in almost every single quantum mechanics textbook, book, lecture. And for example,
also, it looks cool.
Quantum Mechanics for Dummies, it's a pretty popular book. I have it actually. Also has one of its first chapters explaining bracket notation or bracket notation, which is Dirac notation, right? And it's a very integral part of quantum mechanics. And that's why these notations can somehow suddenly become a very important, like F prime, df by dx, right? They all become super important when we're talking about calculus and multivariable calculus, right? So it all depends on the subject you're talking about, the field you're talking about, obviously, and if it's actually useful, one notation versus the other.
Yeah, one thing that I really want to know is why physicists are so obsessed with Greek letters.
I just think because math probably stemmed from Greek. What? Okay, I could from Greece, no, or I don't know, man.
I don't think so.
Wait, weren't the Greek mathematicians geniuses? Aren't they the guys that did everything?
I don't think they made up the they didn't assign
but
lambda
see,
to be wavelength.
If you think about it, right? Math is a language in itself. But if you think about it, that language is kind of Greek. It's kind of a Greek language if you think about it.
I mean, I think I know every single Greek letter now, so that's
cool. Definitely. I definitely know every single Greek letter, and that's purely from math. For
example, why didn't we pick the Chinese alphabet? We would have unlimited
true.
symbols.
That's true.
Right?
That is true. Because, and see, and unfortunately, because of the lack of symbols with the Greek alphabet, what scientists love to do, reuse notation. For example, we saw this in our a math class very recently where we're talking about projectors, pi projectors. And why use the notation pi? Why? There are so many other things, but obviously, pi is such a famous Greek letter. Use pi for everything. So the problem with notation is that sometimes it can get confused. Sometimes it can get confusing, and you can mix it up. So be careful of your notation is also an important rule, for sure.
Yeah. So episode is coming up on 40 minutes.
Yep.
I think that's a good number.
That's a good number. That was a good podcast.
I have pizza waiting for me downstairs, so that's going to be kind of nice. Thank you everybody for listening to episode number 30.
Big 3.
Make sure to drop some questions for the Q&A next week. We will be answering to probably all of the questions.
Absolutely. More questions the merrier.
Yeah, and I don't know if we're gonna get that many, so
hopefully you guys ask. Remember, we have
question.
Instagram, you got comments, and you have our email address. You have everything in the description below, so just hit us up on one of them, and we will respond and definitely answer it. So,
all right,
okay.
This has been episode number 30. We thank you for tuning in. Come back next week, Saturday morning, 10 a.m. Absolutely. We will be here for you, waiting with a discussion. So I'm your host, Parker.
And I'm Ray, and we will see you soon.
See ya.